Welcome to a deep dive into a century of physical chemistry research. You've given us a fascinating mix of papers, excerpts from a Royal Society of Chemistry publication, a groundbreaking study on molecular forces, and research on all sorts of things from mercury clusters to flash photolysis. It's going to be quite a journey.
Indeed, the range of topics is remarkable, shows how physical chemistry kind of bridges physics and chemistry, even touches on biology, always seeking to understand how matter behaves at its most fundamental level.
So our mission today is to pull out the most important discoveries from these papers, understand how they've changed scientific thinking and connect to the bigger picture. I'm sensing some serious aha moments ahead.
Absolutely, and I think what makes this deep dive especially interesting is the time span. Seeing how these discoveries build on each other over a century, it really highlights the evolution of scientific thought.
Okay, let's unpack this. We'll start by setting the stage. You included some excerpts from a Royal Society of Chemistry publication celebrating 100 years of physical chemistry. Tell me more about that.
The Faraday Society, which later became the RSC Faraday Division, played a vital role in advancing physical chemistry. They did this through their journals and, most importantly, their general discussion meetings.
So they created a space for scientists to share their latest findings, debate ideas, and maybe spark new collaborations. Sounds like a hotbed for innovation.
Precisely. These meetings were, and still are, incredibly influential. In fact, the first general discussion focusing on osmotic pressure was held way back in 1907 in London. And here's a fun fact. There's been some confusion about the numbering of these discussions over the years. A recent meeting, numbered 125, was actually the 219th discussion. Goes to show the long and impactful history of these gatherings.
Wow. Talk about a history buff stream. It's incredible to think of all the groundbreaking ideas discussed in those meetings. And it makes me wonder, what were some of the big mysteries scientists were grappling with back then?
Well, one puzzle that intrigued scientists in the early 20th century was the nature of molecular forces. They knew that molecules could attract each other, even nonpolar molecules that didn't have obvious charges. But the prevailing theories at the time couldn't fully explain the strength of these attractions.
It was like a missing piece of the puzzle. They knew the pieces fit together somehow, but they couldn't figure out exactly how.
Exactly. And then, in 1937, Fritz published his groundbreaking paper, The General Theory of Molecular Forces. His work was a game changer. He proposed a new type of attractive force now known as the London dispersion force.
I remember learning about van der Waals forces in school.
Yeah.
But I'm guessing this London dispersion force adds another layer to that understanding.
Yes. London connected this force to the quantum world. He realized that even in nonpolar molecules, the electrons are constantly in motion. These fluctuations create temporary, instantaneous dipoles, meaning one side of the molecule might have a slightly negative charge for a tiny fraction of a second, while the other side is slightly positive.
So it's like a constant tiny shifting of charge within the molecule.
Exactly. And these temporary dipoles can induce opposite dipoles in neighboring molecules, causing them to attract each other. It's like a synchronized dance of electrons, creating attraction out of seemingly nothing.
That's fascinating. So London's theories show that even nonpolar molecules have these hidden fluctuations that lead to attraction. Really highlights the importance of quantum mechanics in understanding seemingly simple phenomena. Did his theory explain anything else?
Yes, it did. London also addressed the repulsive forces that prevent molecules from collapsing on top of each other. He linked this repulsion to the Pauli exclusion principle, which states that two electrons can't occupy the same quantum state.
So this principle puts a limit on how closely electrons can approach each other, and therefore molecules.
Precisely. London's work gave us a much deeper understanding of why molecules maintain a certain distance, and how both attractive and repulsive forces contribute to molecular structure and stability.
It sounds like his work revolutionized our understanding of how molecules interact. So knowing that these fundamental forces are always at play, how did scientists begin to study how atoms come together to form larger structures?
One intriguing area of research focused on metallic clusters. Imagine taking a tiny droplet of mercury, so small that it's made up of just a handful of atoms. What holds those atoms together? That's the question researchers tackled using some sophisticated techniques.
I can imagine that studying something so small must have been incredibly challenging.
It certainly was. Researchers used a technique called a supersonic beam to create clusters of mercury atoms of different sizes. Then they used lasers to ionize these clusters and a time-of-flight mass spectrometer to analyze them, their masses and binding energies.
Okay, let's unpack that a little.
Yeah.
What exactly is a supersonic beam, and how does it help create these tiny clusters?
A supersonic beam is a stream of gas moving at incredibly high speeds, much faster than the speed of sound. Imagine a jet of gas being forced through a tiny nozzle into a vacuum chamber. As the gas expands into the vacuum, it cools down dramatically, and the atoms start to clump together, forming clusters.
So it's like creating a miniature wind tunnel where the atoms are forced to huddle together.
That's a great way to think about it. And the amazing thing is, by controlling the conditions of the beam, researchers can create clusters with specific numbers of atoms.
That's incredible. It sounds like they created a tiny controlled universe to study these clusters. So what did they learn about how these mercury atoms interact?
Well, their findings were quite surprising. They discovered that small mercury clusters, containing less than 13 atoms, are bound primarily by weak van der Waals forces, just like London described. But as the cluster size increases, the bonding transitions to a stronger covalent type.
Wait, so the type of bonding actually changes as the cluster grows? That's unexpected. What causes this transition?
It suggests a fundamental change in the electronic structure of the cluster as it grows. The electrons, which are initially localized around individual atoms, start to delocalize, become shared among multiple atoms as the cluster gets bigger. This sharing of electrons leads to stronger covalent bonding.
It's like a tiny village transforming into a bustling city where everyone is interconnected. So did this change in bonding have any noticeable effects on the properties of the clusters?
It did. The change in bonding from van der Waals to covalent is accompanied by a change in the electrical properties of the cluster. In fact, researchers even proposed the possibility of a Mott transition occurring in these finite systems. A Mott transition is a metal insulator transition, a dramatic change in the ability of a material to conduct electricity.
So as the cluster grows and the bonding changes, it might actually switch from being a good conductor of electricity to being an insulator.
Exactly. The possibility of observing such a transition in a finite system, like a cluster, is incredibly intriguing. Imagine a tiny cluster of atoms behaving like a metal, then suddenly switching to an insulator as it grows.
That is mind-blowing. It really highlights how even tiny changes in size or structure can have dramatic effects on a material's properties. And it makes me wonder about the implications for nanoscale materials. If a tiny cluster can undergo such a dramatic change, what does that mean for our ability to design and control materials at the nanoscale?
That's a great question. It's an area of active research. Understanding these transitions in clusters could lead to the development of new materials with tailored electronic properties. Imagine being able to switch a material from a conductor to an insulator simply by changing its size.
The possibilities are incredible. And it all goes back to those fundamental forces between molecules that London helped us understand. So, speaking of changing scientific thinking, your stack of papers also included a revolutionary technique that changed the way we study chemical reactions: flash photolysis. I'm a bit partial to this one, even though it wasn't directly used in my own research.
I can sense your excitement. Flash photolysis was truly groundbreaking, developed in 1949, opened up a whole new world for studying those elusive and highly reactive species called free radicals.
Before flash photolysis, free radicals were practically impossible to study because they are so short-lived, like trying to catch a fleeting glimpse of a ghost. How did this technique change things?
Before flash photolysis, free radicals were essentially theoretical entities. We knew they must exist, as fleeting intermediates in chemical reactions, but we couldn't observe them directly. Flash photolysis provided the first tool to capture these fleeting species and study their properties.
Okay, so how does flash photolysis work? Sounds like something out of a science fiction movie.
It's actually quite ingenious. Imagine you have a mixture of chemicals that you want to react. You hit this mixture with an incredibly intense but short burst of light, a flash. This flash provides the energy to kickstart the reaction and generate those short-lived free radicals.
So it's like a sudden burst of energy that sets the reaction in motion. But how do you study the radicals if they disappear so quickly?
That's where the second flash comes in. A very short time after the first flash, a second, weaker flash is used to record the absorption spectrum of the reaction mixture. This spectrum reveals the presence and properties of the free radicals that were created by the first flash.
So the first flash creates the radicals, and the second flash captures their spectral fingerprints before they disappear. It's like taking a high-speed photograph of a chemical reaction.
That's a great analogy. And this technique allowed scientists to study free radicals in ways never before possible. They could determine their structures, their lifetimes, how they react with other molecules.
Sounds like a revolution in chemical kinetics. Are there any specific examples where flash photolysis led to important discoveries about free radicals?
Absolutely. One classic example is the study of the CLO radical. Scientists had predicted its existence based on its role in atmospheric chemistry, particularly in the destruction of ozone, but no one had ever directly observed it. Flash photolysis provided the first spectroscopic evidence of its existence, revealing its vibrational structure and allowing scientists to estimate its bond dissociation energy.
So flash photolysis not only proved the existence of the CLO radical, it also gave us crucial information about its properties.
Exactly. And this understanding of the CLO radical was essential for developing models of ozone depletion, ultimately led to international agreements to phase out ozone-depleting substances.
It's a perfect example of how a fundamental scientific technique can lead to insights with real-world implications. What an amazing discovery.
Indeed. Flash photolysis has become a cornerstone of chemical kinetics, paving the way for countless discoveries and a much deeper understanding of how chemical reactions occur.
It makes me wonder, with this ability to capture those fleeting moments in a reaction, did scientists turn their attention to other types of spectroscopy to unlock even more secrets of the molecular world?
Yes, they did. Flash photolysis was just the beginning. And in our next segment, we'll dive into another powerful spectroscopic technique, photofragment spectroscopy. Get ready for a journey into the world of molecular dissociation. Photofragment spectroscopy emerged in the 1970s, gave us a new way to study how molecules break apart. Instead of just initiating a reaction with a flash of light, like in flash photolysis, this technique uses lasers to excite a molecule and then analyzes the fragments that fly apart.
Sounds a bit like a molecular demolition derby. But instead of cars crashing, we're talking about molecules breaking apart at the atomic level. What kind of information can you get from studying these molecular fragments?
It's amazing how much information you can glean from these fragments. By analyzing their energy, the directions they travel in, you can piece together a detailed picture of the original molecule and the forces that caused it to break apart.
So it's like a forensic investigation. At the molecular level, you're analyzing the debris to reconstruct the events leading up to the molecular explosion.
That's a great way to put it. Photofragment spectroscopy allows us to determine things like the excited states of the parent molecule, the strength of the bonds that were broken, and even the internal energy states of the fragments themselves.
Wow, that's incredibly detailed. Imagine knowing not only what pieces a molecule breaks into, but also how fast they're moving, in what directions, and even their internal energy levels.
Really opened up a new window into the dynamics of chemical reactions. We could now study the ultra-fast processes of bond breaking and energy transfer in unprecedented detail.
It's like having a slow-motion replay of a molecular event that happens in a fraction of a second. It must have had a huge impact on our understanding of chemical reactivity.
Absolutely. Revolutionized the field of chemical dynamics, led to major advancements in our understanding of how molecules react and interact.
Okay, so we've explored these cutting-edge spectroscopic techniques that reveal the dance of molecules in incredible detail. But your stack of papers also included research on a more classic area of physical chemistry, gas phase kinetics. Specifically, a paper from 1943 by Butler and Polanyi. That laid the groundwork for determining bond dissociation energies.
Bond dissociation energy, or BDE, is a crucial concept in chemistry. It tells you how much energy is required to break a chemical bond. It's a measure of bond strength. And it's essential for understanding chemical reactions, predicting how molecules will behave.
So it's like a measure of how much oomph it takes to rip a particular bond apart. What was so special about Butler and Polanyi's approach?
They developed a clever technique based on measuring the activation energy for the reaction between iodine atoms and a target molecule. Essentially, they figured out a way to measure how much energy it takes to get the reaction going, and from that, they could deduce the bond dissociation energy of a specific bond in the target molecule.
I see. So by studying the energy needed to initiate the reaction, they could work backwards to figure out the strength of the bond that was broken.
Exactly. While they focused on organic iodides in their initial studies, their work laid the foundation for what's now known as the iodination technique, which has been used to determine bond dissociation energies for a vast array of molecules.
It's like having a molecular ruler. For measuring the strength of chemical bonds, Their work must have been incredibly important for understanding chemical reactivity and stability.
Absolutely. Knowing how much energy it takes to break a bond is fundamental to understanding how molecules will react, what kinds of products will form.
Okay, so we've explored the forces between molecules, delved into the dynamics of chemical reactions, even measured the strength of chemical bonds. Now are you ready for a journey to the vastness of space?
As long as we don't have to wear spacesuits. What are we exploring out there?
We're going to explore the fascinating role of a tiny molecule, Hayes plus Proust, as an astronomical probe.
Haste plus hate. That's a pretty simple molecule. What makes it so special for astronomy?
Well, H plus consists of 3 hydrogen atoms, bonded together with a positive charge. It might seem simple, but scientists had long predicted that it would be a key player in the chemistry of interstellar space. And in 1980, it was finally observed in the laboratory.
So they finally found concrete evidence for this molecule. That had only existed in theory. That must have been a big moment for astrochemistry.
It was a major discovery. And the key to this discovery was its infrared spectrum. Every molecule absorbs and emits light at specific frequencies, creating a unique spectral fingerprint. Scientists were able to measure the infrared spectrum of H+ in the lab, and this spectrum became a powerful tool for astronomers.
I see. So by knowing its spectral fingerprint, they could search for its signature in the light coming from distant objects in space. Did they find it?
They did. And the first place they found it was completely unexpected. Haze plus emission was first observed in the auroral regions of Jupiter.
Jupiter's aurora. That's fascinating. I always associate auroras with Earth. What's H+ doing there?
That's what surprised scientists. It turns out that H+ plays an important role in the chemistry of Jupiter's upper atmosphere, where it's formed by the interaction of charged particles from the sun with hydrogen molecules.
So it's a byproduct of the same process that creates the beautiful auroras we see on Earth.
Exactly. And it wasn't just Jupiter. H+ was later detected in Uranus and Saturn, and even tentatively observed in supernova 1987A.
Wow, this tiny molecule is showing up all over the place. What does that tell us about the universe?
It tells us that H+ is a fundamental molecule in the universe, playing a role in a wide range of astrophysical environments. It's a reminder that the principles of chemistry we study on Earth are at play throughout the cosmos.
That's a powerful thought. So from the tiniest molecules to the grandest cosmic events, chemistry is truly universal.
It is. Now let's bring it back down to Earth and dive into the theoretical realm once again. We're going to explore the transition state method in theoretical dynamics.
The transition state, that sounds familiar. Remind me what that is.
Imagine a chemical reaction as a journey, from reactants to products. The reactants are like the starting point, the products are the destination. And the reaction pathway is the road that connects them.
Okay, I'm picturing a road trip for molecules.
Exactly. And along this road trip, there's a crucial point called the transition state. It's a high-energy configuration that the molecules must pass through in order to react. Think of it as the mountain pass. You have to cross to get from one valley to another.
So it's the highest energy point
Well,
along the reaction pathway, the point of no return, where the molecules are committed to forming products.
that's a great way to put it. And the transition state method, introduced by Wigner in 1938, provides a powerful way to understand and calculate reaction rates. It relates the reaction rate to the properties of this transition state, such as its energy and vibrational frequencies.
So it's like knowing the height and shape of the mountain pass determines how quickly travelers can cross it.
Exactly. The transition state method essentially tells you how easy or difficult it is for molecules to reach that mountain pass and proceed to the product valley.
It's a brilliant concept. By understanding the transition state, you can predict how quickly a reaction will proceed. Did this method have a big impact on the field of chemical kinetics?
It was revolutionary. The transition state method has been refined and extended over the years, but it still serves as a cornerstone of chemical kinetics, helping us understand and predict the rates of countless chemical reactions.
It's incredible how such a theoretical concept can have such a profound impact on our understanding of chemical reactions. Highlights the power of theoretical models to provide deep insights into the mechanisms of chemical transformations.
Okay, so far we've explored the intricate world of molecules and their interactions. But what about mixtures? How do molecules behave when they're all jumbled together?
That's where things get even more interesting. Understanding mixtures is crucial in so many areas of chemistry, from designing new materials to understanding biological systems.
Well, your stack of papers included a 1952 paper by Barker, who tackled the fundamental challenge in understanding liquid mixtures. What was he trying to figure out?
Barker was interested in understanding how the shape and orientation of molecules affect the properties of liquid mixtures. He knew that molecules aren't just tiny spheres bouncing around randomly. They have specific shapes, can interact with each other in specific ways.
So it's like trying to fit puzzle pieces together. The shape and orientation of the pieces matter if you want to make the puzzle complete.
That's a great analogy. Barker developed a theoretical model that incorporated the concept of orientational free energy, which essentially reflects the energy associated with specific arrangements of molecules due to their shape.
So some arrangements of molecules are more energetically favorable than others, depending on their shapes.
Exactly. And his model helped explain why some mixtures behave ideally, meaning they mix perfectly, with no change in their properties, while others deviate from this ideal behavior.
So even in seemingly simple systems like liquid mixtures, there's a hidden complexity, governed by the interactions between molecules. It reminds me of those forces between macroscopic objects we talked about earlier. Are they at play in mixtures as well?
They certainly are. Remember those fascinating forces between macroscopic objects that Overbeek and Sparnay measured? Well, those same forces, now known as van der Waals forces, play a crucial role in the behavior of a special type of mixture, colloids.
Colloids. I vaguely remember that term from chemistry class, but I'm a bit fuzzy on the details. Remind me, what exactly are colloids?
Colloids are mixtures where tiny particles of one substance are dispersed throughout another substance. Think of milk, where tiny droplets of fat are dispersed in water, or fog, where water droplets are dispersed in air.
Okay, so it's like a miniature universe of particles, suspended in another medium. What makes colloids so special?
What's fascinating about colloids is that the forces between these particles determine whether they clump together or stay dispersed. And those van der Waals forces we talked about, they're one of the key players in this intricate dance of attraction and repulsion.
So it's a constant tug of war between forces, determining the fate of these tiny particles. What other forces are involved?
Besides van der Waals attraction, you also have electrostatic repulsion, where particles with the same charge push each other apart. Then there's Brownian motion, the constant random jiggling of particles due to their collisions with the surrounding molecules. And you even have hydrodynamic interactions, which arise from the flow of the surrounding fluid.
Wow, it's a lot more complex than I imagined.
Yeah.
Sounds like understanding colloids requires a deep understanding of forces at multiple scales.
Exactly, and that understanding is crucial because colloids are everywhere, from paints and coatings to food products and pharmaceuticals. We encounter colloids in countless aspects of our daily lives.
Okay, so we've got these tiny particles in a constant state of motion, interacting through a complex interplay of forces. What determines whether they stay suspended, clump together, or settle out of the mixture?
That's the million-dollar question in colloid science, and it's a question that's closely tied to the concept of stability. A stable colloid is one where the particles remain dispersed and don't clump together or settle out, but achieving stability can be a delicate balancing act.
So it's all about finding the right combination of forces to keep those particles happy and dispersed.
Exactly. And scientists have developed various strategies to manipulate these forces and control the stability of colloids. One common approach is to add stabilizing agents, which can be molecules or ions that absorb onto the surface of the particles, either increasing their electrostatic repulsion or creating a steric barrier that prevents them from getting too close together.
So it's like giving the particles a protective coating. That helps them keep their distance from each other.
That's one way to think about it. And controlling colloid stability is essential for countless applications. Think about paint. You want the pigment particles to stay evenly dispersed in the liquid so that the paint applies smoothly, doesn't separate over time.
That makes sense. Or in food products like mayonnaise,
Yeah.
where you want the oil droplets to stay disposed in the water
Yeah.
to create a smooth and creamy texture.
Exactly. Understanding and controlling colloid stability is a key aspect of many industries, and it all goes back to those fundamental forces between molecules and particles.
It's amazing how such a seemingly simple concept, mixing tiny particles in a liquid, can be so complex and have such wide-ranging implications.
It is, and it highlights the interconnectedness of different areas of physical chemistry. What we learn about forces at one scale can often be applied to understand phenomena at vastly different scales.
Now, I can't help but notice that you mentioned liquid crystals earlier, and I know you're fascinated by them, so I'm curious to hear more about these materials that seem to bridge the gap between liquids and solids.
Oh, liquid crystals are truly captivating. We've already touched on Frank's groundbreaking work on the continuum theory of liquid crystals, but there's so much more to explore.
Okay, so remind me, what's so special about liquid crystals? What makes them different from regular liquids or solids?
What makes liquid crystals so intriguing is that they occupy a realm between the order of a solid crystal and the fluidity of a liquid. Their molecules can flow and move around, but they also maintain a certain degree of orientational order.
So it's like a school of fish swimming together in a synchronized pattern, but still having the freedom to move individually.
That's a fantastic analogy. And this delicate balance between order and fluidity gives liquid crystals their unique optical and electrical properties, making them ideal for all sorts of applications.
Okay, I'm picturing these molecules gracefully flowing while still maintaining some sort of alignment. But what controls this degree of order? What factors influence how these molecules arrange themselves?
Well, one of the key factors is the shape of the molecules themselves. Liquid crystals are often made up of rod-shaped or disc-shaped molecules that tend to align themselves along a common direction.
So the shape of the molecules encourages them to line up, like
Yeah.
tiny soldiers in formation.
Exactly. And the degree of order can also be influenced by temperature. As the temperature increases, the molecules have more thermal energy, move around more freely, leading to a decrease in order. In some cases, a liquid crystal might even transition from a more ordered phase to a less ordered phase as you heat it up.
So it's like the molecular soldiers getting a bit rowdy as the temperature rises, breaking formation and moving around more chaotically.
That's a great way to think about it. And this ability to change their order in response to temperature changes is one of the things that makes liquid crystals so useful in displays.
Ah, so that's how they can change their optical properties
Yeah.
and create the images we see on our screens. I'm starting to see how these seemingly subtle changes in molecular order can have such dramatic effects on a material's properties.
Absolutely. And it's not just temperature. Electric fields can also be used to control the orientation of liquid crystal molecules, which is how LCDs work, liquid crystal displays.
Okay, so we can use temperature or electric fields to manipulate the alignment of these molecules. What other factors influence how they behave?
Well, another key factor is the nature of the intermolecular forces between these molecules. Remember, we talked about how the shape and orientation of molecules can affect how they interact with each other.
Right, those orientational forces that Barker described in his paper on liquid mixtures.
Exactly. Those forces are also at play in liquid crystals, and they can influence the stability of different phases, the ease with which the molecules can reorient themselves.
It's fascinating how everything is interconnected, from the forces between individual molecules to the macroscopic properties of the material.
It is, and that's what makes studying liquid crystals so rewarding. It's a field where you can explore the interplay of physics, chemistry, and materials science.
Now, I know we've talked about self-assembly before, but I'm curious how this concept applies to liquid crystals. Do they exhibit self-assembly as well?
Oh, absolutely. In fact, self-assembly is one of the defining features of liquid crystals. Remember those rod-shaped or disc-shaped molecules we talked about? Well, those shapes are often driven by a combination of attractive and repulsive forces that encourage the molecules to pack together in specific ways.
So the shape and interactions of the molecules guide them to assemble into those ordered structures. It's like a molecular construction crew, building those intricate formations.
That's a great way to think about it. And depending on the specific molecules and the conditions, they can self-assemble into a variety of phases, each with its own unique degree of order and optical properties.
So from the tiniest details of molecular shape and interactions to the macroscopic properties of the material, it's all interconnected. It makes me appreciate the elegance and complexity of these materials even more.
They truly are fascinating, and their applications go far beyond just displays. Liquid crystals are being explored for use in sensors, actuators, even smart materials that can change their properties in response to external stimuli.
It's incredible how our understanding of these materials has led to such diverse and innovative applications. And it all goes back to that fundamental drive to understand the nature of matter and how it behaves.
Absolutely. And in our next segment, we'll dive into another fascinating aspect of physical chemistry, electrochemistry. Get ready to explore the world of reactions that involve the transfer of electrons. Electrochemistry is a fascinating field. Explores the interplay between chemistry and electricity. It's all about reactions that involve the transfer of electrons, like those that occur in batteries and fuel cells.
I remember those reactions from chemistry class, oxidation and reduction where electrons are lost or gained. But I have to admit, the details are a bit fuzzy now. Can you refresh my memory on how electrochemistry works?
Absolutely. At its core, electrochemistry is about harnessing the flow of electrons to drive chemical reactions. or using chemical reactions to generate electricity. Imagine a simple electrochemical cell, like a battery. You have two electrodes made of different materials, immersed in a solution that conducts electricity.
Okay, I'm picturing two metal rods sticking into a beaker of liquid.
That's a good starting point. Now, at one electrode, a chemical reaction occurs that releases electrons. That's the oxidation reaction. At the other electrode, a reaction occurs that consumes electrons. That's the reduction reaction.
So electrons are flowing from one electrode to the other through the solution.
Exactly. And this flow of electrons is what we call an electric current. The chemical reactions at the electrodes provide the driving force for this current.
So in a battery, the chemical reactions are essentially powering the flow of electrons, which we can then use to power our devices.
Precisely. And by carefully choosing the materials for the electrodes and the solution, we can control the voltage and current of the battery, as well as its capacity and lifespan.
It's amazing how we can harness these fundamental electron transfer reactions to create such useful devices. Now, your stack of papers included a 1947 paper by Randalls that addressed a challenge in studying these electrochemical reactions. What was he focused on?
Randalls was interested in measuring the rates of very fast electrochemical reactions, the kind that happen in the blink of an eye at the interface between an electrode and a solution.
I can imagine that trying to study something so fast at such a tiny scale must have been incredibly challenging. What was his solution?
He developed an ingenious technique based on impedance spectroscopy. This technique involves applying a small alternating voltage to the electrode and measuring the resulting current response.
Okay, so instead of using a constant voltage, he's using a voltage that's constantly fluctuating.
Exactly. And by analyzing how the current lags behind the voltage, you can extract information about the kinetics of the electrochemical reaction. It's like sending a series of electrical pulses and listening for the echoes, revealing the hidden dynamics of the reaction at the electrode surface.
So the way the current responds to those voltage fluctuations tells you something about how fast the reaction is happening. It sounds a bit like using sonar to map the seafloor.
That's a great analogy. Randalls' technique allowed scientists to determine rate constants for electrode reactions, providing valuable insights into the kinetics of electrochemical processes. It was a major advance in the field of electrochemistry.
I can see how that would be incredibly useful. Being able to measure those rate constants must have opened up all sorts of new possibilities for studying and understanding electrochemical reactions.
It did. It laid the groundwork for modern electrochemical techniques, used to study a wide range of processes, from corrosion to energy storage in batteries.
So from understanding how corrosion works to improving battery performance, this technique has had a real-world impact. It's amazing to see how fundamental research can lead to such tangible advancements.
Absolutely. Now, speaking of real-world impact, let's revisit the world of catalysis. We've already touched on Taylor's emphasis on understanding the catalyst itself, but there's so much more to explore in this field.
I'm ready to dive back into the world of catalysts. Remind me, what exactly is heterogeneous catalysis, and why is it so important?
Heterogeneous catalysis is all about reactions that occur at the interface between different phases. Imagine a solid catalyst, like a metal or a metal oxide, in contact with a gas or a liquid mixture of reactants. The catalyst surface provides a platform where reactant molecules can absorb, interact, and ultimately react to form products.
Okay, so the catalyst is like a meeting place for the reactants, where they can come together and react more easily.
That's a great way to think about it. And the specific properties of the catalyst surface, such as its electronic structure and the presence of specific atoms or defects, can dramatically influence its catalytic activity. It's like having different types of dance floors, some conducive to slow waltzes, others to energetic jigs.
I love that analogy. So not all catalysts are created equal. Some are better suited for certain reactions than others.
Exactly. And researchers have devoted a lot of effort to understanding what makes a good catalyst, how to design catalysts with specific properties for specific reactions.
I can imagine that this is a really important area of research, especially for industries that rely heavily on catalysts, like the chemical industry.
It is, and there have been some incredible advances in the field of heterogeneous catalysis. For example, techniques like X-ray photoelectron spectroscopy, XPS, and scanning tunneling microscopy, STM, allow us to probe the electronic structure and atomic arrangement of catalyst surfaces. with incredible detail. It's like having a magnifying glass for your catalyst, allowing you to see the intricate details of its surface and how it interacts with reactive molecules.
So we can actually visualize what's happening at the atomic level
Yeah,
on the surface of the catalyst. That's incredible.
it is. And these advancements have allowed us to design more efficient and selective catalysts for a wide range of applications, from producing fuels and chemicals to removing pollutants from exhaust gases.
It's a powerful example of how fundamental scientific understanding can lead to technological innovations that have a real impact on our everyday lives.
Absolutely. And one of the most impactful examples of heterogeneous catalysis is the Haber-Bosch process. This process, developed in the early 20th century, allowed for the large-scale production of ammonia from nitrogen and hydrogen.
The Haber-Bosch process, I remember learning about that in history class. It was a major breakthrough, had a huge impact on agriculture, right?
It was. Ammonia is a key ingredient in fertilizers, and the Haber-Bosch process made it possible to produce ammonia on an industrial scale, which revolutionized agriculture, contributed to the growth of the global population.
It's incredible to think about the impact that this one chemical process has had on the world. What makes the Haber-Bosch process so special from a catalysis perspective?
The key to the Haber-Bosch process is a carefully designed iron-based catalyst that facilitates the reaction between nitrogen and hydrogen. This reaction is extremely slow under normal conditions, but the catalyst lowers the activation energy barrier, allowing the reaction to proceed at a much faster rate.
So it's like the catalyst is providing a shortcut for the reaction.
Yeah.
Making it much easier for the nitrogen and hydrogen molecules to combine and form ammonia.
Exactly. The development of the Haber-Bosch process was a triumph of chemical engineering, and it showcases the power of using catalysts to drive important industrial reactions.
It's a remarkable example of how we can manipulate reaction conditions and use a carefully chosen catalyst to make an otherwise impossible reaction industrially feasible. It makes me think about all the other possibilities out there. What other reactions could we unlock with the right catalyst?
That's a great question, and it's one that drives a lot of research in catalysis. There's a constant search for new and improved catalysts that can drive reactions more efficiently, use less energy, and produce fewer waste products. It's a field with enormous potential.
It sounds like the possibilities are endless. Now let's zoom back into the molecular level and explore another fascinating aspect of chemistry, stereochemistry.
Stereochemistry. The study of the three-dimensional arrangement of atoms in molecules. It's a crucial concept for understanding the properties and reactivity of molecules, especially in biological systems.
I remember learning about isomers in chemistry class. Molecules with the same chemical formula but different structures. But remind me, how does stereochemistry fit into this picture?
Well, stereoisomers are a specific type of isomer where the atoms are connected in the same order but arranged differently in space. Imagine two molecules with the same atoms, connected in the same sequence, but one is the mirror image of the other.
Okay, so it's like having two identical sets of building blocks but assembled into different structures. They might look similar at first glance, but their arrangements in space are different.
Exactly. These mirror image molecules are called enantiomers. And even though they have the same atoms and bonds, they can have vastly different properties. It's like having a pair of hands. Your left and right hands are mirror images of each other, but you can't perfectly superimpose one on top of the other.
I see. So even though the building blocks are the same, the way they're arranged in three-dimensional space can make a big difference. How do these differences in spatial arrangement affect the properties of the molecules?
They can influence a wide range of properties. For example, they can affect how a molecule interacts with other molecules, including biological targets like enzymes and receptors. One enantiomer of a drug might be effective, while its mirror image might be inactive or even harmful. They can also affect a molecule's physical properties, like its melting point, boiling point, even its smell or taste.
So even if the chemical formulas are the same, these mirror image molecules can behave completely differently. It makes me wonder, how do chemists deal with these differences in stereochemistry when they're making molecules?
That's a great question, and it leads us to an important technique called chiral resolution. Chiral resolution is the process of separating these enantiomers from each other, allowing chemists to isolate and study each form individually.
So it's like sorting through a box of gloves, separating the left gloves from the right gloves. But how do you separate molecules that are essentially mirror images of each other?
There are various techniques, often relying on the fact that enantiomers interact differently with other chiral molecules. For example, imagine a special type of filter that only allows one enantiomer to pass through. while blocking the other. Or a chemical reaction that selectively reacts with one enantiomer, converting it into a different molecule that's easier to separate.
So it's like having a molecular sorting machine that can recognize the subtle differences between these mirror image molecules. Why is chiral resolution so important?
It's crucial in many fields, especially pharmaceuticals. As we mentioned earlier, one enantiomer of a drug might be effective, while its mirror image could be inactive or even harmful. So being able to separate and purify the desired enantiomer is essential for developing safe and effective medications.
That makes perfect sense. It's incredible how something as seemingly abstract as the three-dimensional arrangement of atoms can have such a profound impact on a molecule's properties and its potential applications. It really highlights the importance of understanding stereochemistry in chemistry and beyond.
It does. And it brings us to the end of our incredible journey through a century of physical chemistry research.
Wow, what an amazing deep dive. We've covered so much ground. From the fundamental forces that govern molecular interactions, to the intricate self-assembly of molecules, the dynamics of chemical reactions, the mysteries of the cosmos, and the challenges of controlling matter at the nanoscale. What stood out to you from this collection of research?
For me, it's the remarkable progress that's been made in understanding the nature of matter. We've gone from grappling with basic concepts like molecular forces to manipulating matter at the atomic level and designing materials with unprecedented precision.
I completely agree. It's inspiring to see how scientific curiosity and ingenuity have led to so many breakthroughs that have transformed our understanding of the world and led to countless technological advancements.
And it's not just about the past. What excites me the most is the future of physical chemistry as we continue to develop new tools and techniques to probe the mysteries of the molecular world. Who knows what amazing discoveries await?
Absolutely. It's a field that's constantly evolving, and I can't wait to see what the next century of research brings.
Just imagine the possibilities. We might uncover new forms of matter, develop even more sophisticated catalysts, and design materials with properties we can only dream of today.
The future of physical chemistry is brimming with potential. And for you, our listener, we hope this deep dive has sparked your own scientific curiosity and inspired you to keep exploring the wonders of the molecular world. Until next time, keep asking questions and keep diving deep.